So did you switch on the?
I'm recording this session.
Okay. Got it. That's good. Okay. Let us start with a brief introduction of Tamil Nadu Science Forum by me. So let me first welcome you all on behalf of Tamil Nadu Science Forum. I'm extending a warm welcome to you all. Today we are going to have a webinar on the topic on nuclear fusion. So the title is, could we build a miniature sun on Earth? The prospect of nuclear fusion. This is the title we are going to handle. This lecture shall be delivered by Professor P.A. John. So Professor John will be introduced by Dr. Subhasri Deshian, science correspondent in Hindu. So we have with us Professor TRG and Professor Ramanujam. So he will be joining soon. So this meeting shall be in English because the topic which we are going to handle is very tough to deal in Tamil, as well as the speaker is also not conversant with Tamil. So naturally, it's going to be in English. So we will try to have a brief introduction about Tamil Nadu Science Forum. Before that, I'll be spending a few minutes about the PSL, then I'll go to the TNSF. So after this introduction, Dr. Subhasri will introduce the speaker and followed by the lecture, and we'll have the Q&A question answer session, and we are expecting to wind up everything before 5 p.m. So this is the program today. So coming to the PSL, PSL is part of Tamil Nadu Science Forum, and it started functioning in 2018, although the Tamil Nadu Science Forum is functioning from 1980 onwards. So PSL came into existence when we decided to strengthen the activities of TNSF in the higher science area. So we have conducted 47 lectures so far, and it's going to be the 48th. Mostly last 4 years, we have covered all the three Nobel Prizes every year. So that means 3 into 4, 12 lectures on Nobel Prizes, which we have covered. And apart from that, we have extensively covered the aspect of COVID-19. So it is around some 12 lectures on COVID-19. So it starts from PSL 18. So all of them are an online meeting. So it's the time to wind up our online and go to the offline meeting. But still, we have a lot of followers in online meeting. Then we are continuing with that. Hopefully, next meeting is going to be in offline meeting. And as usual, in any virtual meetings, we are following some ground rule. All of us are expected to switch off your mic and until the question answer session open. The speaker will deliver the lecture. After that, we will have the question answer section. You can write your questions in the chat box. So during the question answer session, your question will be read by Dr. Deshian, Professor Deshian. She is going to moderate the meeting, and she will read the question one by one. And those who want to chat with the speaker directly, you can raise the hand as well. With regard to the Tamil Nadu Science Forum, it was started in 1980 by few scientists, science enthusiasts, and science activists. And we have the founder member, Dr. TRG, who was instrumental in starting this organization. When he was doing his PhD in Madras University, he was initiating this. He was one among the group to initiate the starting of the TNSF. So TNSF, during 80s, early part of 80s, it was confined to only hall meetings and have similar lectures what we have now. After 1986, it has been turned into a different path. So when the literacy campaign has started, TNSF is getting involved in the total literacy campaign, and it started expanding its activities beyond Chennai, and it goes throughout Tamil Nadu. And now we have the branches in all part of Tamil Nadu, all district branches, and we also have the local branches in cities, villages, and districts. So that way it has been extended, and now we have some 360 members and full-fledged state-level organization taking, and the activities are expanded into 6 different verticals. I would say that those verticals are one in the science propagation, the other one is in science publication, and third one is in education, fourth one is in youth for science, and the fifth one is the women equality, women in science, what we call it is in Tamil as Samam. So these are all the areas which all of us can get into that. If any of you are interested in get into the science, any of those activities, you can straight away fit into one among the 6 verticals. And this PSL fall within the group of science propagation. So we are popularizing the science. So we work with the state level group, which is meant for propagating the science popularization group. So that way the organization has been structured, and all of us has any those who are having interest in part of this organization, you can become a member of Science Forum, and you can take up any of those activities coming under any of the 6 verticals. No. So it's not confined to only 6. No, it's going to get expanded, because day by day, a lot of things are exciting things are coming up. We have to open more such verticals. As of now, we have only 6 verticals. And after this meeting, we would like to get your feedback of this webinar, which we are going to post a form, Google form. So I will be providing you the link in the chat box. And please fill up the form, providing your contact details, your opinion of the program. So your contact details is helpful for us to communicate with you for our future programs. And we will assure that we'll keep your contact confidential, and that shall not be shared with anyone else. And it shall be used only for communicating our programs only. In the meantime, we also have a Telegram group meant for PSL. You can join the Telegram group. I'm going to provide you the link for Telegram group as well. We also have a Google mail group that's called the Popular Science Lectures at google.com, googlegroups.com. I'll be providing you the link for that as well. I can provide you the link. You can send a mail to that. You will naturally become a member of that group. And if any of you are dropped from this meeting due to any technical reason and unable to get back to the meeting, we recommend you to get into the YouTube broadcast as well. The link will also be provided in the chat box. Please save that link as well while the meeting is on progress. So with that, now let me ask Dr. Subhasri Desikan to introduce the speaker.
Hello, everybody, and good afternoon. It's a great pleasure for me to introduce today's speaker. It's a matter of pride, pleasure, and privilege to be part of Popular Science Lecture of Tamil Nadu Science Forum. The lectures are really very popular, and I would strongly urge you to follow this group. So let me briefly introduce Professor John. When I approached him for this lecture, he readily agreed, and I was so happy to do that. And it's a very proud task today to introduce him to the audience. Professor John held the Meghnad Saha Chair in Plasma Science and Technology at the Institute for Plasma Research in Gandhinagar, IPR. He joined the Physical Research Laboratory in Ahmedabad in 1972 and helped establish the Plasma Physics Program in 1982. This initiated the Thermonuclear Fusion research in India by building the first Indian Tokamak. The activity evolved into the Institute for Plasma Research in 1986. In 1997, Professor John set up the Facilitation Center for Industrial Plasma Technologies to develop commercially viable plasma-based technologies and to link IPR with the industries. Professor P.I. John also took part in the negotiations leading to India becoming a member of the International Thermonuclear Experimental Reactor, Aether project. He was a member of the Science and Technology Advisory Committee of Aether and represented India on the Aether Council. In 2008, he developed the National Fusion Program for funding universities and educational institutions in research in fusion sciences. There are 2 books he has written which are worth mention. His book, Plasma Sciences and the Creation of Wealth, was published by Tata McGraw-Hill in 2005. Another book, Plasma Processes for Energy and Environment, was published by Lambert Publishers in November 2017. Professor John is a fellow of the Indian Academy of Sciences and the Government of India honored him with Padma Shri in 2010. His interest transcends science. He writes blogs, he writes poetry and paints also. His work is available at the website pukadale.com. And that is for the introduction of the speaker. If you have any questions following the talk, you can put the questions in the chat box, or you can raise your hand and you can either ask it yourself, or if you put it in the chat box, I can convey it to the speaker. Now, Professor, please, we invite you to come and give the talk.
Thank you, Shubhashri, for that kind introduction. I must compliment the Tamil Nadu Science Forum for their efforts in popularizing science, and I thank them for inviting me to give this talk, which I shall now start. Just 1 minute. I have. Okay, let me share the screen. As you know, the life on Earth is sustained by the energy from sun. And naturally, one would like to ask, what is the source of this energy? What makes the sun shine? Naturally, again, we would, at least the scientists among us would try to ask whether we can reproduce these sun-like conditions on Earth. So that's what I meant by the question, could we build a miniature sun on Earth? And it is these questions that we shall discuss in this talk. We know that the equilibrium of the sun is due to the balance between the heat generated from nuclear reactions at the core of the sun against balanced by the gravitational compression of the entire bulk of the sun. So unless there is this balance, the dimensional stability of sun would be in a problem. Now, if you look at the sun in more detail, you will see that at the core, the temperature goes to 15 million degrees. And the pressure at that core would be something like 340 times atmospheric pressure. It's enormously compressive environment with extremely high temperatures. It is these conditions which enable nuclear fusion reactions to happen in the sun. And that is what is powering the sun. So the question as to what makes the sun shine was first answered by Professor Arthur Eddington in 1926. And he said that stars draw their energy from the conversion of hydrogen into helium by thermonuclear fusion reactions. But the details were actually brought out more later in 1939 by Hans Bethe in his theory on proton-proton chain reaction. So what he said is that hydrogen does not get converted to helium in one step, but in a number of steps. So first, two hydrogen nuclei fuse and creates deuterium nuclei, and they fuse to create helium, 3 helium nuclei, and they further react to produce 4 helium, the regular type of helium, alpha particles, and also releases other particles in the reaction. So this is exactly how the sun, at the core of the sun, these reactions happen. Now, why? The question is naturally, is it possible to recreate these conditions on Earth? The extremely high temperature and pressure conditions, can they be recreated? In fact, it has been recreated whenever we explode a hydrogen bomb. This is exactly what happens. A chemical explosion starts off a fission bomb, and the X-rays produced by the fission bomb contained in this cavity compresses a fissile material sponge containing deuterium and tritium. And once that is compressed to very high temperature, it undergoes thermonuclear fusion reactions, and the bomb then explodes as a hydrogen bomb. So people have transiently recreated sun-like conditions on Earth, but the question is, can we do it on a sustainable basis, on a continuous, peaceful manner without exploding bombs? So let's look at the reaction which is happening inside this thermonuclear weapon. It is a fusion between deuterium, the isotope of hydrogen, with the tritium, another isotope of hydrogen. And what comes out are alpha particles with 3.5 MeV energy and 14.1 MeV neutrons. So bulk of the energy is carried by neutrons. So for a input of 20 kilovolt in energy, kilo electron volt in energy, the output is more than 17 mega electron volt. So 1,000 times multiplier in the fusion. So the yield is, let's say, 1,000 times more than what was put in. Now, one would like to ask this question: why is it so difficult to achieve these reactions? Why do we have to go to the core of the sun or explode a hydrogen bomb for fusion reactions to happen? So that becomes clear if you examine the interaction between nuclear particles, like protons. At a long distance, there is a electrostatic repulsion, the Coulomb repulsion between same charge particles, so which does not allow the same particles to come together very close. But if by some means you are able to bring them very close, with something like order of 10 to minus 15 meter, then the nuclear forces take over, which are attractive forces. So the nuclei then would further come together and fuse into each other. So the trick is in crossing the Coulomb barrier, which is the fundamental problem in fusion. Now, as you can see here, one way to bring the nuclear particles together is to put it in the core of sun, like at extremely high pressure. So everything would be compressed to extremely small dimensions, and nuclei would approach each other, and the temperature would further enable fusion. But if we cannot do that, another way to do is to fling one particle against another with very high energy. So if you are able to do that consistently, that means throw one particle against another. This is equivalent to saying that you keep all the particles at very high temperature, so they move about with very high kinetic energy, and then they come within a distance closer than 10 to minus 15 meter, then they would fuse. So the requirement of fusion then would be to bring particles close enough, which can be done only at extremely high temperature. That is the reason why this is called thermonuclear fusion, fusion which happens at extremely high temperatures. Now, as I said, we have already done it in terms of an explosive realization, but a sustainable way people have been searching for, and two approaches have come in this manner, in the way of looking at whether we can reproduce these conditions. And one is called the inertial confinement fusion, or ICF. And here, as the name sounds, this is a more general realization of the hydrogen bomb. There also the confinement is inertial, because as soon as the bomb explodes, the particles are no longer kept together, so they lose confinement. So this is what happens in an inertial fusion device. Use powerful lasers or particle beams to compress and heat a tiny deuterium-tritium pellet to extremely high temperatures so that fusion would happen. And as long as the pellet keeps together, fusion reaction would happen, but the hot pellet would expand and get lost by expansion, and the fusion then naturally would come to stop. So this is the inertial confinement fusion. And second approach is to take a plasma at this temperature, 100 million degrees or so. 20 kilovolt is like 200 million degrees, but in a sustained manner you can achieve fusion at 100 million degrees. And if you keep it together for long enough time for fusion reaction to happen, then again you have possibility of recreating what happens in the sun on a sustainable manner. So people have done calculations, found that for deuterium-tritium fusion to happen, you require a temperature of 100 million degrees on a steady time basis. So that is what now the second option. Now let's look at these things in a more detailed manner. As I said, once the intense lasers became available, one of these ideas of inertial fusion became a possible thing to try on. So idea here is that you take this powerful laser, break it up into a number of beams, irradiate a pellet containing deuterium and tritium, actually frozen so that it is DT ice, and the pellet absorbs the laser radiation at the surface. At the outer surface ablates away, and there is a shock wave which is produced as a reaction to the ablation. So this shock wave would compress the matter in the pellet to its core and heat it up by compression, and the core, once it acquires the temperature and other conditions required for fusion, would fuse together and explode as a micro miniature hydrogen bomb. So this is the principle of inertial fusion, realizable because very high power lasers are available. So let's look at what is the situation. But the people found that in direct heating, that is irradiating the pellet directly with the laser beams, is not a good idea, because it leads to non-spherical compression, non-uniform compression. Why? Because the number of beams available to us is finite. So a surface does not get uniformly irradiated, and very likely some part would get irradiated more than other parts, and so the compression would not be uniform. So the pellet would actually break up rather than fuse. So in 1972, John Nichols from Los Alamos, Lawrence Livermore, came out with this idea that instead of directly irradiating the pellet with the laser beam, why not convert the X-ray, convert the laser light into X-rays? How do you do that? You allow the laser beams to fall on the inside of a cavity with the gold coating on the inner surface. This is called a hole room, and gold would absorb the laser light, evaporate, and become a very hot plasma. And the hot plasma emits X-rays, and so basically the pellet at the center of this hole room would be bathed by the X-ray flux generated out of laser plasma interaction on the gold surface. So this would start the compression. Like we said earlier, the irradiation of the pellet creates compression wave, which allows the pellet to be fused at the center and create thermonuclear conditions. So this is this indirect drive method as against a direct drive practiced by the earlier experiments. There are still experiments going on in Japan, for example. Direct drive is tried in Rochester laboratory in US. Also, direct drive is practiced. So there are adherents to both these schools of inertial fusion using lasers. So with US dominance in laser, in very high power lasers, US leads the construction of high power lasers and using them for inertial fusion. As you can see here, in 1973, they had something like 100 joule laser.
Professor, you need to unmute.
Professor, we cannot hear you. I think you're muted again. Sir, you are muted, I think. We cannot hear you.
Sir, you're muted. Can you unmute? Sebastian, you can call him.
Professor John? Professor John, I think you're muted. We cannot hear you.
Okay. Now, was it muted now?
Now it's clear.
Is it muted now?
No, sir. No,
I
no.
don't know.
Now we can hear you.
Okay, but earlier, was I not audible?
When you started talking about Janus, 100 joules, that time it got...
Okay, yeah, all right. Okay, so you're not lost me completely. Okay.
No, no.
All right, so Janus is 100 joule laser. And since the laser operates for a few nanoseconds, the power is enormous. This joule divided by nanosecond would be the extremely large powers. And then came the Argus laser, Shiva, Nova, and now the National Ignition Facility has a laser which has a energy of 1.8 megajoule, which is again, if you look at the time of operation, this is enormous. 1.8 megajoule is equivalent to 10 to the 15, a quadrillion watt, 10 followed by 15 zeros. That much power the laser is able to deliver. And this is also is broken up into 192 beams. So their facility, NIF in Lawrence Livermore laboratory, has these 192 channels of laser, which is brought to the reaction chamber, and the pellet, the whole ROM, is situated in this reaction chamber. And as I said, the indirect scheme operates here, and the laser is converted to X-rays, and it X-ray flux irradiates the pellet and drives it to fusion. Now, this is something which happened recently. They had an experiment in which as you see here, all these beams getting inside the whole ROM, the gold plasma is generated, which converts the X-rays into laser light into X-rays, which irradiates the pellet, and you get fusion to happen within the pellet. Now, this is the idea here. There are some numbers here. The temperature reaches 10 to the 5th, 10 to the 8, 100 million degrees. And density is the order of 1000 grams per centimeter cube. And like initial density is order of 1 gram per centimeter. So 1000 times compression. And the pressure is again 10 to the 11 atmospheres. You don't have to go to the solar conditions of billions of atmospheres, because you can balance against that. The temperature that you achieve here is much, much higher than the solar temperature. That's 15 million degrees, and you're reaching 100 million degrees. And this picture here is a whole ROM, like a pencil cutter size, and inside is the pellet situated, something like 2 millimeter diameter. The whole technology of creating these pellets is also very, very complex. They are diamond coated because it would absorb laser light more efficiently, and so on. And so history was created on August 8, 2021, when researchers at Lawrence Livermore produced actual fusion, a burning plasma, liberating 1.3 megajoule, comparable to the input power. And you had what is called a burning plasma. But this is far from becoming a reactor, because many more steps have to be taken. See, this pellet experiment is done one experiment in a week, whereas a actual reactor would require many, many pellets to be burned, fused in a second. So you have to cross from a feasibility demonstration to actual reactor demonstration, and it will take a lot more research and development and time. So, but let's hope that that would happen soon. Okay, now let's come to the second approach, which is the magnetic confinement approach. And here, as I said, the deuterium-tritium plasma has to be produced at 100 million degrees. And since it's far away from thermodynamic equilibrium, it will try to expand and lose that energy. So the plasma cannot be allowed to lose the heat. And you need to confine it. And the criterion that is necessary for fusion to be realized is what's known as a Lawson criterion, which means that the density, that is kilograms per meter cubed, and temperature in 1000 Kelvin, and the confinement time in seconds has to exceed a number called 10 to the 21, which is a Lawson criterion number for fusion to happen on a sustainable basis. So this is the goal, and let's see what we can, how we can reach there. So magnetic confinement means the plasma is kept together for a much, much longer time than inertial confinement. And many ideas have been tried out to get a magnetic confinement scheme working. And what has succeeded is called the Tokamak, which is a Russian invention. It actually comes out of this Russian word, toroidal. Actually, it means in English, toroidal chamber with magnetic coils. And this is invented by the well-known Andrei Sakharov and Igor Tamm at the Cryostat Institute in Moscow in 1950. There were many, many other ideas which were competing to be to demonstrate confinement, to demonstrate working confinement. And Tokamak is the most successful scheme. And so by around 1960, most of the laboratories became adherents of the Tokamak scheme. But basically, Tokamak is a transformer. Let's see how it works. This is a transformer magnetic core, and you have primary exciting currents in this coil. And so magnetic flux changes. When the flux changes, there is a electric field generated in this direction, and the electric field will break down the gas in this vacuum tube. This torus is a vacuum tube. It's a cylinder bent into a circle, and the electric field creates a current and heats up the plasma, and the hot plasma is confined by magnetic field generated by these coils, toroidal field coils, because it creates a magnetic field in this direction. So this is basically how the Tokamak works. Now let's look at it in more detail. As I said, the plasma current is generated by the exciting the primary, and the plasma current generates a magnetic field around the plasma current in this is called the poloidal magnetic field. And this is a poloidal magnetic field, and the toroidal field coils like this create a magnetic field in this direction. So the combination of the two fields, the axial field and the poloidal field, is a spiraling magnetic field. So if you have the spiraling magnetic field which goes around and around, because they may never close on itself, so actually you are creating magnetic surfaces. And you know that particles are confined to magnetic field lines or to magnetic surfaces. So the plasma particles can stick to these magnetic surfaces and be confined. So that's the trick of the Tokamak. The combination of this toroidal and poloidal is essential because plasmas are well known for being very unstable. If you create this very hot plasma, it doesn't like to remain in this torus, but would break out of the torus. So it is actually imprisoned by this magnetic surface created by the combination of the magnetic fields. So that is the miracle that the Tokamak creates. The other problem is that once you create the plasma and confine it, you have to heat it to a thermonuclear temperature, 100 million degrees. How do you do that? Initially, the current itself heats the plasma to very high temperature, but as the plasma gets hotter and hotter, it becomes more and more conducting. So it's becoming as good a conductor as copper at some temperature. So then you cannot any longer heat it by currents alone. So you have to heat the plasma by other means. One of them is to shine very high power electromagnetic waves into the plasma, and the electromagnetic waves creates resonances with the plasma waves and transfer energy from the wave to particles. It's quite like the microwave oven, except that there are plasma resonances which are used here. The other method is to inject very high energy neutral particles, beams of neutral particles, neutral hydrogen or neutral deuterium, into the plasma. The incoming energetic beam exchanges charge with the plasma particles, and the plasma particles then leave. The beam particles are now ionized, and then it sort of adds up to the matter inside and adds up to energy. So neutral beam heating is one way, radio frequency heating is another way. There are other tricks as well for plasma heating, but these are the more common methods of plasma heating. So with these ideas, people started building tokamaks, and one of the very successful machines is the joint European torus, which was built in Culham laboratory in England, in Oxford, and it was built in 1983, and this is one of the very successful tokamaks. So you can see the transformer coils here like a transformer frame here, multiple frames to drive very high currents. And these are the toroidal field coils. And inside you can see the torus in which the plasma would be created. When the machine actually works, we can see the plasma gets created here. The plasma is so hot that its radiation you cannot see, except the cold outer edges of plasma, which is cold, it emits visible light. The inner core of the plasma at 100 million degrees or near that would be emitting X-rays. So you cannot actually see it. You cannot see the glow. You can see the glow of the outer colder regions of plasma. So column tokamak or jet is one of the very successful tokamaks. And let's see what happens in a machine like jet. How does the tokamak discharge work? Here I have shown the transformer, the primary here. So this is the current in the primary. You increase the current to something like a 100 kiloampere in the primary, and you suddenly disrupt that current, bring it down to zero. So you create a di by dt, which creates a magnetic field dB by dt, which creates a induced voltage, which is shown here. This is induced voltage in the torus, which breaks down the gas, initial neutral gas into plasma, and heats it by driving up a current, which is a current driven up by the electric field, and the current is then held steady. You have many tricks like gas pumping to control the density and current and so on, and the energy is stored within the plasma. This is exactly how a tokamak discharge works. This is a figure from a machine at Garching, IPP Garching, a machine called ASDEX. So let's see what happens further. Again, in a historic experiment on 21st December 2021, jet was able to create fusion-like conditions and produce 59 megajoules of energy over a pulse of 5 seconds. 5-second pulse. As you saw earlier, the pulse is a long-term pulse. And this is a much better performer than something which happened in 1997. That was the first time jet produced fusion neutrons, fusion in the device. And this time it has improved itself. And this is a great success story. More than double the 22 megajoule released in 1997, as against the 40 megawatt into 5, that's 200 megajoule power input into the machine. More important than that, the actual energy, what was shown by jet is that the jet performance obeys a scaling law. That's the various parameters can be changed, and you get a performance indicator that's called the scaling law. And jet actually obeys the Tokamak scaling law, which means that you can project to the size of the machine that would work as a full break-even machine. Okay, so jet is still not a complete full energy recovery is not there. So if you want to generate more energy than you input into the fusion device, you have to improve the performance. And this scaling law allows us to predict the parameters of a machine which should do exactly that. And that is a machine which we call Aether, International Tokamak Experimental Reactor. And this is a jet, something like 8 meter. And Aether across is 17 meter, so almost double the size of the jet. And it's a 6 meter, the plasma major radius. And the magnetic field is also higher, 5.3 Tesla. The current is much, much higher than jet current. jet had 4 megaampere, Aether would have 15 megaamperes, million amperes flowing through the plasma to heat it and so on. So this is a jet Aether machine, which hopefully all of us believe would demonstrate that you can get fusion on a sustainable basis in the laboratory and possibly convert, get energy out of the device. Now, Aether has an interesting story. At this is the time of the Geneva summit. That is the time when Americans and Russians were beginning to approach some form of friendship. And the General Secretary Gorbachev proposed to President Reagan that to demonstrate goodwill, they should do something together, which is to build a thermonuclear fusion reactor. And immediately Europe and Japan joined this effort. And what is called initially called the INTOR, International Tokamak Experimental Reactor, which later became Aether, was formed. The INTOR design was completed in 2001, and later on further improvements were made. And recently in 2006, two more countries joined, China and South Korea and India, and the Aether came into being in 2006. China had joined earlier. India was the last to join, and Aether became at least a reality in terms of a purpose. Now you see, more than 50% of the world population is represented by the 7 countries which is supporting Aether, and it is being built in a place called Cadarache in the south of France, where the famous painter Saha used to paint this part of France. And this is where the sun on earth would start shining. So it's a very optimistic picture of Aether. So the purpose of the Aether is to demonstrate scientific and technological feasibility of fusion power for peaceful purposes, and all these countries work together. Now, Aether Tokamak is here to get an idea of how big this is a man standing here. So it's enormous, something like 37 meters high, much bigger than an apartment building. And there are these toroidal field coils, the torus, the vacuum vessels, and so on. And the outermost thing that you see on entering the Aether hall would be what is called a cryostat. It is a vacuum chamber, the world's largest vacuum chamber, which will house all the superconducting magnets. So without the cryostat, the magnets cannot efficiently work. And this cryostat is being built by India. So the first thing that you see in Aether when it's completed will be an Indian-made cryostat. And everything else will be inside because this is made of steel. You cannot see anything else. So this is how Aether would be built. Actually, about 50% of the cost of the Aether would be borne by Europe, whereas the balance would be shared among other 6 countries. So we will pay about 10% of the Aether cost. And how do we do this? We don't give that money. We actually convert that share into equipment. So we build the cryostat, for example. India builds a cryostat. India builds a number of other things. And Europe builds the part of the vacuum chamber, magnet coils, and so on. So various people, various countries would collaboratively build various parts of the machine, and everything would be brought to Cadarache, and it will be assembled there, and the machine would come into being. So this is a great idea in collaboration, international collaboration. And in India, the Aether project is funded by the Department of Atomic Energy and implemented by the Institute of Plasma Research through an agency called Aether India, which is the purpose is primarily to deliver parts to Aether. This is a cryostat, for example. It's a very impressive machine. It's actually made up of many, many parts which will be welded together at the Tokamak site. It's fabricated by Larsen and Toubro and shipped to France. They also builds very sophisticated power supplies as part of our delivery. And this is the Indian activity. We have built the Cryostat Workshop, and India supplies cryogenic lines. It will all be assembled here. Cryogenic means liquid helium components will be assembled here, and water cooling system, everything. A number of things are being done. And ITER timeline is like this. You start, for example, 2006, ITER is formed and the buildings happened. And by 2000, ITER machine assembly is started in 2018. And by 2025, it is hoped that ITER would be fully assembled and the first plasma would be produced in ITER. So 2025 would be only beginning of ITER operation, because once the plasma is produced, it will be tuned up until 2032 for full Deuterium-Tritium operation. That is another phase, because DT operation means neutrons and the machine would become radioactive. So that is another phase of DT operation will continue until 2040. So there is a long way to go from now, 2022. By 25, hopefully it will start working, and then 40. It actually will hopefully demonstrate that this is a working principle for fusion reactors to be built. And let's look at the conviction behind this, reason behind this conviction. This is the parameter. This is the triple product Lawson parameter, and this is the temperature, 1 million degrees, 10 million degrees, 100 million degrees. So these are all machines. As I said, ITER became a very popular device, and everyone started building tokamaks. And then you have these big machines like ITER or TFTR or JT60. These are all big tokamaks operating in the world. So many machines like this. The interesting thing is that private sector startups have joined ITER, the fusion game. So recently there was this very convincing proof that very compact machines. This is very, very small compared to ITER. They showed that such machines can produce 100 million degrees by using very, very high power, the magnets which are not cryogenic, not liquid helium, magnets operating at higher temperature, but superconducting magnets. And this is what's called a spherical tokamak, another variant of tokamak. And recently also laser fusion, another idea has come about. This is a hydrogen boron fusion. You convert a plasma into a beam of protons, which would fall on a boron target, and then it generates fusion. Proton boron fusion would happen at very, very high temperature, 200 million degrees. But the advantage is that it is neutron free, and so it's very clean, unlike tokamaks, which will be full of neutrons. So these are all examples of how private sector has been now attracted to fusion, and they are joining the fusion game. And I have drawn up here a timeline for fusion. 51 is when Sakharov and Tam invented the tokamak, and Baba actually made a prediction to 55 that in 10 years, 20 years, fusion would be realized. But that was not a correct prediction. 58, second UN conference on peaceful use of nuclear energy fusion meetings. And in 1968, in the conference in Novosibirsk in Russia, Russians convincingly demonstrated the superiority of tokamaks as against other approaches. And so everyone got the tokamak fever, started building machines. And the first presentation of inertial fusion ideas in 1971. Both Russians and Americans came out with the ideas. And start of INTOR, Gorbachev-Reagan summit, ITER agreement, and now recently tokamak and laser fusion experiments. And so 25 is the next timeline. We will see what happens in 2025. So what do we conclude out of this? We are certain that fusion is the answer to the 21st century energy demands. International effort is accelerating. Both approaches, inertial and magnetic confinements, are showing success. India is participating in this very adventurous and exciting trip to realize fusion. But beyond all this demonstration, reactor technologies have to be developed. So people say that even after realizing fusion, another 10, 20 years would pass before an actual reactor would come into being. So do not expect fusion power to light up your homes before 2050. That's what generally consensus. But the interesting thing is private sector, including a company in Pune, has started fusion startups. So that's a good sign. So let me conclude here and stop here. Thank you very much.
Thank you, sir, for that very enlightening talk. So would anyone like to ask any questions among the people present here?
No, we have one question in the chat box.
Yeah. Let me read out that question. This is from Balasubramaniam KM. He says, sir, I have the following 3 questions. One is, would there be any unreacted plasma after the fusion reaction? If so, how would the remaining unreacted plasma be extracted from the heating chamber? Then the last part is, are there any dumping mechanisms for the unreacted remnants of the plasma beam?
That's an interesting question. Actually, very small part of the fuel would be reacting. Very substantial part is unreacting. But unreacting means it's deuterium, which you can release, no problem. But tritium is valuable. So tritium has to be extracted from the unreacted part. But that is a very standard technology. You can allow tritium to condense on cold surface and get it back. So helium also can be extracted by filters and so on. So all of the plasma which is not reacted can be extracted. But as I mentioned, very small part of, because this is a kind of a statistical thing, reaction it happens only in small part of the fuel. So that is my answer to your question.
I have a question. You mentioned that the plasma will become very, it'll be not visible only in the edges because it's cooler and the center will not be seen. Yeah. Will the center be transparent or will it be opaque?
It'll be transparent. Yeah, you can actually see through the hot machine on the other wall.
Oh, okay.
Okay, yeah, but you see, the emission is Wien's law says that higher the temperature, higher the frequency of radiation, right? So at the temperature 100 million, most of the emission would be in X-rays. Okay, now in sun, this happens in the core. By the time that X-ray comes out, it would have been, it would have got dissipated into lower wavelengths. So that's why you get the sun to emit visible. But in an actual reactor plasma fusion machine, a good part of plasma would be in X-rays, emitting in X-rays. In fact, that is one of the methods to diagnose the plasma, to measure the X-ray flux from the plasma.
There's a question from Ramanujam. I have read that China is going for closed tritium fusion cycle. What are the challenges for them?
Well, China has built a machine called East, which is a very good performing tokamak, and they have reached very high temperatures also. So they are certainly one of the leading technology contenders in fusion machines. East actually also very recently showed that a plasma can be confined for 1,000 seconds, unlike a jet machine, which the plasma is confined for 5 seconds. Because ultimately, if you can get the tokamak to become a steady state machine as against pulse machine, tokamak being a transformer has to be necessarily started as a pulse. But you can sustain the current by radio frequency, current drive, and so on. And then tokamak becomes a steady state reactor. There's nothing like a steady state reactor which is for performance and efficiency. Because if you run the machine only once in a few minutes, the efficiency, overall efficiency is poor. So they have shown that they can operate the machine for 1,000 seconds. So that's a big step forward.
Any follow-up questions, Ramanujam?
No, I was just wondering whether India has similar plans.
We built a machine called, it's a superconducting tokamak, SST, superconducting steady state tokamak, with a much smaller time scale as a demonstration. But it is not performed as well as Chinese machine has, which is a fact. Because we start, in fact, in fusion, we started much later than any of these countries have. But we have actually picked up quite fast if you look at our performance over the time. But there is a machine, there are two machines in Ahmedabad. One is called Aditya, which is the first machine that we built. The second is SST1, which is a superconducting steady state tokamak.
If I can go to the next question, Naveen RS is asking this question. Sir, how will this be sustainable when compared to current nuclear fission reactors? Like how much percentage this will reduce the nuclear waste, which is the current nuclear reactors problem, like in Kudangular nuclear reactor?
Excellent question. As I said, neutrons will be a problem in DT fusion. So the chamber would get radioactive, steel would get radioactive, and so on. So the machine, operating machine, would be radioactive. And so you have to take care of radioactive waste of the entire machine. In fact, a good part of Aether's future would be in decommissioning the machine, because everything would be radioactive. But the hope is that fusion ideas like proton-boron fusion, if they succeed, then you do not have neutrons at all. It becomes very clean and sustainable fusion reactor. But proton-boron is into the future. But if you look at, as the time scale, the performance I showed earlier, we have come a long way. So it's quite likely that we can also go a long way in the future into ideal fusion devices like proton-boron fusion.
Next question is by J. John Paul. China's artificial sun has set a new world record after superheating a loop of plasma to temperature 5 times hotter than the sun for more than 17 minutes. Will machines like East in the long run become a problem, because here we deal with high energy and temperature?
No, the high energy and temperature is a misleading thing, because that is confined to the core of the machine. Because magnetic fields do not allow the plasma to come to touch the wall. They allow, then confinement would be lost. So you can confine 100 million degree plasma very safely in the core of the tokamak by magnetic fields. Okay, so there's not a problem. There's no problem because of the plasma heat melting anything.
Okay. That's all the questions in the chat box. Can we go to the direct questions now?
Yeah.
Yeah, there is one more question, I think. This is a question about whether the Earth goes around the sun in 365 days, but other planets, how many days around the sun? So the question, the answer is that each planet takes a different time to go around the sun. But should we, do you want to comment on this, Professor John?
This is not at all relevant to my talk.
Okay. This is a astrophysics question, and maybe we can save it for future PSLs. Any, yeah, we can open the floor to the questions if.
Madam, shall I answer that question?
Yes, please.
Mercury takes 88 days, and probably Venus takes somewhere around 220 days or something, and Pluto takes 248 years to go around the sun once. So the Pluto was actually discovered in the year 1930. So far, it has not completed even one orbit after its discovery. So that is the, but request the viewers to ask relevant questions to the talk, okay? Because we just don't want to kill the interest of a student. That's why it's answered.
Yeah, okay. Thank you. Thank you. Vijayan sir, can we go?
We can ask the audience to directly chat with the ask the questions.
If you can go for gallery view, I can know who's raising the hand and so on.
Yeah, no one has raised the hand so far. That's what I feel. TRG, you have any questions? TRG,
sir, alone attempt for creating this artificial sun in Earth in India.
I did not get the question.
So can India singly create this artificial sun in India?
Well, that's our hope. By joining Aether,
yeah,
our hope is that we can learn the technology as a working reactor is being built, and then replicate that in India and build reactors in India. That is the hope.
Okay, hope the best.
Sir, sir, could you stop sharing screen? Then I think the gallery.
Yeah, okay. All right. Okay, stop sharing. Yeah.
Yeah, now I think we can. Yeah. So.
Naveen has raised his hand.
Yeah, Naveen, can you unmute yourself and ask the question, please?
Yes, sir. What all are the high? Is there any higher studies map has been created, or like higher studies research we can do related to the fusion, nuclear fusion, the engineering, and in the science part?
Well, Institute for Plasma Research allows students to work for the PhD. So below that, we don't have any involvement. But there are many institutes like IIT Delhi, I understand, gives plasma physics courses. And I am not sure about other institutions. But you can work for a PhD in Institute of Plasma Research. We also promote research in universities by funding them in plasma physics and fusion related activities.
Thank you, sir.
Sir, in the case of the International Space Station, there is a huge collaboration between countries, and they say that the cost and other things are so prohibitive that one single country cannot independently do this. Is it possible in the case of the Tokamak and the fusion reactors? Is it possible for a single country to have the technology, the know-how, and the money to invest in a reactor?
Well, I think it's a matter of once a convincing reactor demonstration, a physical demonstration happens, it's a matter of the further things are all engineering. See, why are the private players coming into this? Because they see an opportunity of building reactors, not necessarily all of them for power, but for radioactive isotopes and so on, neutrons, using neutrons. So there will be various ideas of realizing a fusion reactor. And as I said, these high temperature superconductors have opened the field totally, because unlike the Aether, which is so huge that it may wonder whether one country alone can build it, but the machine in this Tokamak fusion facility is very small compared to Aether. So it's kind of, when I saw the picture, I thought it's very doable kind of machine. So if they succeed, that would be the kind of reactors that will be built. But everything will scale down because all parameters are going up. Magnets are going more powerful. And so it's possible that we may get compact reactors in the future. And also possible that other ideas than Tokamak also can work. There is a simple idea of compressing a pellet mechanically. That is, a company is doing that. They have designed a compressing scheme which will spherically compress a pellet by mechanical means. It's a hammer, kind of hammer. So, very radical ideas are coming in. And once the startups come in, they are very imaginative. They will come out with very, very radical ideas. Unlike Aether, which is a very, very stately kind of a slow-going project, the private sector will radicalize the fusion situation.
I think Jam has a question. Jam, would you like to ask?
Yeah, I mean, maybe it's a bit extraneous. I wanted to know about the role of computer simulations and the work done in India on that, because I would have thought that, on the surface of the reactor, there must be, all kinds of tests to be made, transients, very high loads, and so on. So how,
that's a very, very good question. Unfortunately, I'm not a computer simulation expert, but very, very good work is going on in IPR. And one of my colleagues, Shekhar, and he is a computer expert, and he has actually put up a video on the YouTube.
I see.
On one of the conferences of mega computing for fusion applications. Okay, I can trace out that and send it to you through someone. Okay, through Vijayan, and so you can take a look at that video presentation, because that's one of the conference presentations.
Yeah, because I feel that this is one area of technology development where we have to do enormous amounts, much more than.
Yeah, but things are moving there. A number of groups are involved, and IPR itself has a very powerful computer in which is used for simulation and activities and so on. Okay.
Right. Thank you.
Naveen has asked us to put the video in Telegram. Let me put that now. Once I get the link, I can share it with through the PSL. That's not a problem.
Yeah, I'll send it to.
Okay.
I want to ask one question. You have mentioned that like different fusion reacting experiments have produced energy of different scales, like the Brookhaven people, and then the Aether and so on, the English experiment and so on. So what is the major breakthrough that is needed to advance it to? Is it going to be a gradual process, or do you need a breakthrough in some field?
Well, realizing Aether would realize that breakthrough also, because Aether is so designed that it will demonstrate a working fusion reactor, except that it will not produce energy, electricity. Okay, so that is the next step. Convert Aether into a working reactor means you have to convert neutrons into heat and the steam cycle and so on. But Aether, if Aether works, then you will not need any further breakthrough, except breakthroughs in making the machine compact and more less costly. Aether cost is enormous. I don't think any country would actually build a machine like that.
Okay.
But technologically or scientifically, Aether would prove that fusion works.
Okay. There's a question from John Paul. What is the type of heating that will be more efficient to heat plasma? Is it ohmic heating or radio frequency heating, etc.?
Well, as I said, ohmic heating will not take it to 100 million degrees, because by the time you heat up, the plasma becomes conducting. So you cannot heat ohmically. Okay. So you need to use radio frequency power or neutral beam or things like that. So a combination of all of these would be required to heat the plasma to the required 100 million degrees. Ohmic alone is not enough.
Any other questions, TRG? Anyone else? So would you like to...
Now I have put the link for all those things. Now one is, now I appeal all the audience to become member of Tamil Nadu Science Forum. I have put the link for to become the member of Tamil Nadu Science Forum. That's a Google form, and the subscription is ₹30. That can be paid through Google Pay. We also provided the number, mobile number for Google Pay. So you can become a member of our PSL Telegram group. No, I also put the link for the Telegram group. You can also become a member of our Google group. I also put the mail ID for the Google group. So we also put the feedback of this link for the feedback form. So please fill up the feedback form, leave your name and your contact details. That will be helpful for us to include you in our mailing list, and we'll definitely keep it secret, keep it confidential, and we'll use it only for communicating our program.
So on my part, I shall pass on to Vijayan a PDF file of the talk and a link to that YouTube program on mega scale computing. We can pass it on to whoever wanted that. Okay.
Yes, sir. Thank you, sir.
Thank you so much for that very interesting and very fascinating talk. Many aspects were new to us and it's very enlightening. Thank you so much.
No, we want to bring it in booklet on this fusion technology in Tamil local language. There was a demand.
Okay.
So this should be your input, your lecture is very useful for us to bring that booklet. So Tamil Nadu Science Forum will bring that on soon.
Okay.
They are working on it. Yeah.
Okay. Thank you very much.
So with that, let us go for a vote of thanks. Let us have a formal vote of thanks. Now, Balasubramaniam is having something. No? Yeah, he's clapping his hand. Okay, all right. Okay, so as a formal vote of thanks, let me thank Dr. P.A. John for accepting our invitation and delivered a great lecture. It was a wonderful lecture, and audience are enjoying the lecture. And it's going to be in our YouTube channel. Now, PSL has a YouTube channel. It's going to be there. So thank you very much, sir. And my next thanks go to Dr. Subhashree. She's moderating this event and she's reading all the questions and organizing that. Now, she's not only moderating it, she is the one who bring you to this, bring Dr. John to this event. Thank you, Subhashree. And our special thanks go to our patron, Dr. Ramanujam and Dr. TRG, who are the founders of this PSL. All the 48 lectures have been has been done without has been done with the help of Dr. Ramanujam and TRG. Had this they are very much helpful in organizing these things, and my thanks to Dr. Ramanujam and Dr. TRG. And I also thank all my EC members. You know, I'm being the secretary of this PSL, and my special thanks to all my EC members who are participating in the EC meeting and organizing the event successfully. My thanks to all the participants who has patiently here and ask the questions and make the event live. My special thanks go to Sundar, who is the technical person who is behind the scene and operating all the devices and making this event successful. Thank you, Sundar. With that, let us close the event. Thank you all. Thank you very much.
Thank you.
Thank you. Thank you, sir.
Okay, thank you very much.